big old shiny crown. I'm taking all the country, throwing my weight around. I'm feeling really godlike. I can do both anything.
Geology.
Lord, Lord, you know that it's good to be king.
Geology and geology. Yes, this is Mini Geology, the weekly radio show about geology, the relationship between our beloved discipline and society. And here I am today, again in the KPFT HD2 studio in Montrose, Houston, Texas. Hello everybody, all the geologists and non-geologists around the world and up there in the International Space Station where you astronauts can also listen to KPFT HD2 channel. And today we have with us the research professor Sean Gulick. He's a professor at the Jackson School of Geosciences, which is part of the University of Texas in Austin. According to abundant geological evidence, an asteroid roughly 10 kilometers across hit the Earth about 65 million years ago. This is in the Yucatan Peninsula. Yeah, in Mexico. So this impact made a huge explosion in the crater, about 150-180 kilometers across. Well, the debris from the explosion was thrown into the atmosphere and severely cooling the climate and leading to the extinction of roughly 3/4 of the species that existed at that time on the planet, including the dinosaurs. So many asteroids of this type, they pass through the inner solar system and they also cross the Earth's orbit. And some of these, they could potentially hit the Earth sometime. But anyhow, that was my super summary about the topic we're going to talk today, again with the professor, the research professor, Sean Gulick. Sean, are you there with us?
I am. Thank you for inviting me.
All right. We are very pleased to have you on board in here.
Well, thank you.
Sean, so tell us, what did I say wrongly about this super short explanation?
Well, you had a few numbers a little off, but other than that, it was a good summary. The crater is a little larger, and the date of the exact timing of the impact has been updated in the last few years due to some really nice argon geochronology work on volcanic ashes right, close to the boundary and so on.
So tell us, what are the right numbers?
Yeah, so the exact age is now 66.0 million years ago, so it's moved back by about 500,000 years based on the latest dating. And the size of the crater is roughly 200 kilometers across, so it's a little bit bigger than I think you said in your intro.
All right, so obviously Sean in here, he knows way better than anybody these things because he was a chief or co-chief of an IODP expedition. Exactly, I think the number is 364, where he went offshore to recover cores from the crater that we are talking about. So, Sean, do you want to give us some basic information about what is that you study?
Well, absolutely. So I'm part of a very large team now. We represent, I guess, we're about 80 scientists who are all studying the most recent research into the Chicxulub impact crater. So, it goes back a long time in terms of the discovery of the crater in the early 90s, which kind of basically confirmed the possibility that Alvarez and others were correct in saying that the extinction at the end of the Cretaceous was caused by asteroid impact. And so there's been lots of work on this in terms of geophysics, both gravity and magnetics over the 90s. And then in the early 2000s and into the 2000s, there were some onshore drilling efforts without actually being able to really see the target being drilled into because none of the seismic data within that karst landscape onshore was very good. So what's really new and different that's happened in the last just couple of years is using offshore seismic data that we collected in the 90s and 2000s. We actually targeted what's called the peak ring of the Chicxulub crater. So this is a sort of a discontinuous ring of mountains that surrounds the center of the crater. And we drilled using a lift boat, which normally is used just to service drilling platforms. But in this case, we used it as our drilling platform. So we lifted it up about 15 meters or 45 feet or so above the water and put a land mining rig hung off the bow of the vessel, and using funding basically from the International Ocean Discovery Program and the International Continental Scientific Drilling Program, we then drilled for 2 months into the peak ring, taking continuous cores starting at about 500 meters or 1,500 feet below the sea floor. And all the way down until we ran out of money at about 1,335 meters.
And how much money did you have to do that?
How much what? How much money?
Yes.
Yeah, it was about a $10 million project.
And then you ran out of it.
Yeah, that's right. And so what we succeeded in that is to actually sample, starting at about 48 million years ago, so sample in the Eocene, right through the Paleocene-Eocene thermal maximum, this very hot time that occurred 55 million years ago, and then through a thinner section of the Paleocene, that sort of 10 million years immediately after the impact, and then right into both impact-generated deposits, which were super exciting, and then into the uplifted basement crustal rocks that made up the peak ring.
So tell us again, Sean, why it was so important to go and drill exactly at that location, which, by the way, we should explain that the crater is so huge that it's partly onshore and partly offshore, right?
That's right. So at the time, 66 million years ago, it was entirely a marine target. It was probably at shallowest water anywhere there was maybe 100 meters, and it was as deep as probably 2 kilometers on the northeast side. So it was sort of a carbonate ramp type environment that it hit. But nowadays it is half onshore and half offshore, and so of course the best images are all offshore. But as to why we picked the peak ring, that was the result of a workshop in 2005 where we basically asked the larger science community, if you had to drill only one place, where would you go? And the resounding answer came back, go to this place, this peak ring, because all of the impact crater modeling, whether it's sort of geologic models of how craters form on the moon or computer models using codes left over from the nuclear bomb simulations known as hydrocodes or ISAIL and things like that, they differed completely in how the craters formed, and the place that differed the most between those models was the peak ring. And so by sampling the rocks of that ring, we could basically test the fundamental way in which impact craters act as a geologic process, how they change the surface of planets. So that was point one. Point two was by drilling up on a high, we could get hopefully a complete record of sort of the recovery of life in the crater, away from hopefully lots of slumping and things like that might disturb the record. And that would get us a chance to talk about what does the drilling at ground zero tell us about the extinction event itself? And then third point was that's a good spot to drill if you're interested in the post-impact effects on the biosphere in the crust. So in other words, something known as the deep biosphere or the subsea floor life, if you will. It's thought to be a big hydrothermal system would be kicked off by the impact crater, and this might be the perfect kind of environment for thermophilic or heat-loving microbes to kind of move in and inhabit the crater after it formed.
And that was a very interesting part, and we're going to talk later on the relationship between life after the impact. But before that, I would like to ask you, what are the links with society? You were talking about $10 million, and I was wondering who funded it, and the entity, institution who funded it, why it was interested into it.
Yeah, well, so it's actually very broadly funded in the sense that the International Ocean Discovery Program has more than 20 member nations. Actually, I think it's 25 member nations now, all over the world, whose scientific organizations that are governmentally funded. So things like in the United States, the National Science Foundation, for instance. They all contribute together to this international set of organizations to go after scientific drilling targets of particular significance. And in this case, you know, we kind of stood on three legs of the stool. So one is, if you're interested in, I guess we'll take it in order, if you're interested in the way that planets' surfaces change through time, well, on Earth, that's all about plate tectonics, erosion, things like that, because impacts are less important now, you know, with our particularly active surface environment. But on all the other rocky planets of the solar system, and presumably other solar systems as well, impact cratering is the dominant thing that affects the surface of the planet. And therefore, we kind of should understand exactly how that process works. And in situations in the future where we are going to land and maybe create bases, understanding those processes will help us assess where the resources might be within craters in order to better have human habitation on other planets in the future. So that's point one. Point two is to really understand the way life works on Earth. It's very useful to look at a time when life really, you know, took a whack. So, you know, exactly what happened 66 million years ago that caused 75% of life to go extinct, and then how it recovered is a great way to understand the stresses that, you know, the whole Earth system in terms of life on it can be put under, and then how does it respond. So that was important. And then point three is, if we actually want to understand the origin of life, one of the theories is that the origin of life occurred very early on Earth's history and may have had something to do with these impact-produced hydrothermal systems. So it would be worth studying a more recent version of that kind of ecosystem to think about evolution of life on Earth.
I see. So it seems that the entire academia was interested into this project, from the discipline studying life to the ones studying planetary science. Were there other parts of society, or academy is the main part of the society interested into that, and the funding also came from academy?
Well, so you could make a fairly strong argument that the general human interest of the death of the dinosaurs maybe outweighs just about all other science topics that you can pick.
Yep.
You know, it certainly, you know, subsequent to this drilling and all our discoveries that we had, we've had, I think it's now 7 TV documentaries and, you know, probably hundreds of interviews and articles written about the expedition, simply because there's so much excitement about space rocks and dinosaurs, to put it plainly spoken. You know, so I think there's a real reason to simply explore these fundamental processes that can affect things so greatly, such as end, you know, the reign of organisms that ruled the planet for 200 million years, whereas we've only been sort of around for a couple of million years. So, you know, I think that's part of what drove this interest. But then there are these real-world effects, like because of our research, we can make now very strong arguments about where would you go on the moon or on Mars if you wanted to see the deepest rocks now at the surface. And it turns out that would be the peak ring of these big craters.
Is it useful for your research, this much attention that you get because of the merging of these two spectacular topics that everybody knows?
I guess useful in the sense that it causes excitement and interest, you know, and it adds a bit of pressure on all of the researchers involved to work very hard and get their papers out rapidly, because, you know, they know that there's a lot of other people also interested in the topic. So in that way, it's useful. And, you know, it's, of course, these topics are really fun to talk about. So, you know, it's great that we can use something like Chicxulub and the you know, KPG, as it's now called, the Cretaceous-Paleogene Boundary Extinction Event, as an educational, a geoscience education topic, is something that gets people excited, whether it's 5 minutes in an elevator or it's your grandmother, you know.
Tell us again the exact pronunciation of the name of the crater.
Well, in English, people say Chicxulub, or Spanish usually. In Mayan, they would actually say Chicxulub, because the CX is an SH sound in Mayan.
And what does it mean?
Well, it means tail of the devil, actually. Just kind of a funny name, but it wasn't. The crater was simply named for the towns that were closest to the center, the geographic center of the crater. And there's actually both in the Yucatan in Mexico. There's a Chicxulub Puerto on the coast and a Chicxulub Pueblo a little bit inland. And actually Chicxulub Pueblo is pretty close to the exact geographic center of the crater.
Is there any knowledge that the old civilizations before this century, they noticed that geomorphological feature?
Well, certainly what they noticed is actually a much more modern effect of the crater, which is these cenotes, which are water-filled sinkholes. And it turns out that the inner ring of the crater, so the crater rings, if you will, are actually giant, if you will, normal faults that span out tens of kilometers away from the crater. So there's sort of an inner basin, and then there's a big inner ring of the crater, which is made of faults, and then there's another grouping of faults that we call the outer ring, and then there's even a third grouping of faults we call the exterior ring. And the diameter of the crater is actually measured to the outer ring of faults. But the inner ring of faults, because it's a huge change from sort of a basin into much more shallow Cretaceous limestones beneath, causes a major effect on the subsurface water flow. And so the rain that fell along the area of the inner ring, even though this thing was completely buried, found the inner ring faults and made a series of caves basically all along the inner ring of the crater. And these caves eventually worked their way up to become sinkholes that were water-filled, or so-called cenotes. And so the Mayans, in particular, knew about this ring of cenotes and viewed them as sacred, and actually, carried out sacrifices in those cenotes that were, in the geographic pattern that they were because of the crater lying beneath.
And you talk about, and we talk together now about the involvement of academia and also the attention that the population, societies in general, they give to this topic. What about nationalities? Is this something that is led by United States, or Mexico is co-leading the project? And are there other countries that are interested into this?
Yeah, so the International Ocean Discovery Program projects like this are absolutely international. There are participants from all sorts of different countries. So in our case, we had 32 scientists participate as originally part of the expedition, but then those who requested additional samples and added on to their expertise afterwards, plus all the students and postdocs and advisors of those people, totals us up to closer to 80 people. And I think we, within that, have at least 16 countries represented. The leaders of the project were Joanna Morgan from Imperial College in London, and myself at the University of Texas at Austin. But our third kind of partner in crime was Jaime Urrutia Fukugauchi, who's at the National University of Mexico, and he was sort of the chief Mexican liaison to make sure that this thing went off without a hitch on the Mexican side. And we had 3 Mexican scientists sail as part of the project. So
very interesting. What about if I am a student and I want to study the samples that you recover, or I want to study this topic? What should I do?
Well, there's, I think, a lot more to be done on the cores that we collected. We collected 835 meters of core, so there's been a lot done on them already, but there's a lot more material to be worked on. Plus, it's causing us to go back and look at the cores on land, because now they're in much better context because of what we know from the offshore, as well as causing people to go back and look at outcrops where the Cretaceous-Paleogene boundary is exposed in interior Mexico, for instance, or even here in the Brazos River in Texas. And so, all of those are sort of research opportunities, I think, for students and postdocs to join into the effort.
So, Sean, research professor Sean Gulick, professor at the Jackson School of Geosciences, we're talking with him today. I would like to ask you about your involvement in this so exciting topic. How did you end up doing this thing?
Well, so I originally did it because I'm a primarily marine geology and geophysicist. In particular, I use a lot of seismic reflection data and acquire my own data. And so I got brought on the project in the early 2000s to both start envisioning how we might do a drilling project on this, but also to go and collect a grid of seismic reflection data with an academic seismic ship. I think in 2005, we collected these data, and so did lots of interpretation of, where the faults were in the crater and exactly where the peak ring was and so on. And in particular to start to build the hypothesis tests that we would go after with a drill bit. For instance, one set of hypotheses about how peak rings form were that they came from the collapsing sides of a crater, and they said they would just be made of shallow rocks. And the other set of hypotheses based on computer modeling was that, in fact, the entire crater acts like a rock being thrown in a pond, where you have this big splashing upwards after it hits, and then that upward splash kind of collapses outwards. And the peak ring in that model will be made of the very deepest rocks brought to the surface, having moved tens of kilometers to get there. So, that was a great hypothesis test. You put a drill bit in the peak ring. Is it made of limestone, or is it made of basement rock? So those are the kind of things we developed over a decade or so as we made the case for this drilling.
And did you follow the entire, I imagine, a lot of red tape in here, more than 10 years since that conference that you mentioned in 2005 until you went offshore with the ship, I think, in 2016?
That's correct, yeah. In fact, our first proposal, the very first proposal went in 1999, but I think the first one I helped write was 2001. So, we had 15 years of proposal writing before we actually succeeded in getting this to happen.
And what was the turning point when at the very beginning, I thought, I probably think that people, they didn't care that much until you reach a point where the importance was so much that they start listening to you and funding you?
Yeah, I think that's a good question. I think the turning points came from the better seismic images of the target and the better explanation of the clear, goals and the clear hypothesis tests that we could answer from a single drill site, despite, within this 200-kilometer monstrosity of a crater. And it was hard to sort of say, initially we said, we need 6 holes to answer this, and, that's $200 million, so that's not going to happen, right? So then we had to work our way up to how can we do it for the littlest amount of money and effort, but get the most scientific outcomes out of it. And so that was, once we got to that sort of winning strategy, I think then the tide started turning. And it was a matter of details and exactly when it would happen and how long we would get to drill, things like that.
Was it more important to demonstrate very clearly or to explain very clearly your hypothesis, or it was more about the implications of what you were doing?
I think I would say both. The implications, like why drill, why spend the money, is an obvious thing. You always have to explain. But then you also have to explain how it is that your particular site you've picked and the particular depths you can reach in the time allotted will actually answer the questions that you set out to answer. So, you really have to do both halves of the equation. So you have to understand enough about the drilling and the logistics and the expenses to know what's realistic. And then you have to be able to explain the broader implications of the excitement of being able to do the work in the first place. So why drill here? Why drill a crater? Why not drill somewhere else with the resources available to this international program? And you do so to a team of many reviewers. You go through a panel process where probably in the end, 100 pairs of eyes have reviewed these proposals before they go forward.
I see. I was thinking more than what is very exciting is like to test your own hypothesis or the hypothesis of your team that you're working with, and then the implications you come up with the implications later on because they ask you we need implications.
No, you've really got to say why drill from the very beginning, as well as where to drill and how is it that where you have picked is going to answer the exciting questions and very clear hypothesis test that you've set forward. The harder hypothesis test to lay out was, what are we going to learn about the extinction of life by drilling at the crater? And that was a little bit of a debate within the community. The better records may be farther away from the crater than within the crater. And I think that's because there was a view that the crater would just be a wasteland. So why go there to look at the recovery of life? And it turned out that was one of our greatest surprises when we drilled, is that we actually found, something like 130 meters of rock deposited within a single day. But then we found a slower return of normal sedimentation, and within about a meter of that time, so maybe within just a few years, we found burrowing organisms in the seafloor. So life came back to the crater effectively within just a few years, and that was a huge surprise.
Wow. So tell us about the discoveries. Now the material is still fresh there, but do you already have some discoveries that you can share with us?
Yeah, we've already published. I think we've submitted something like 13 papers at this point already, because it's been a super active team. So our very first paper was one that said that the peak rings form by the same mechanisms that these computer modeling codes had suggested, which is that they in fact do undergo sort of a liquefaction style process without ever becoming a liquid. It's referred to as acoustic fluidization. So in other words, the asteroid hits and it instantly opens a hole that's, in this case, would have been 100 kilometers across and 35 kilometers deep, all the way down to the mantle, and then it would have rebounded up 10 plus kilometers into the air, and then collapsed outward to form this peak ring, while the sides kept collapsing outwards even farther to form multiple rings to the outside. So, that was sort of the confirmation based on the drilling of the peak ring and discovering, in fact, it was made of granite, that was brought from at least 10 kilometers below the surface and brought up into this ring of mountains. So that paper was the very first one out of the gate. It kind of answered our very first hypothesis test that we laid out in the proposal. The second paper.
Let me ask you, Sean. Let me ask you about your feelings when you discovered this thing. How did you feel? When did you really realize that it was like such?
Well, we actually realized it on the rig floor. I mean, limestone and granite look very different, and so as soon as the cores came up and we cut the ends of the cores to section them, and we could look and see that it was highly fractured granite, we immediately knew that one of those two answers was correct. In fact, we started writing that first paper before we ever split the cores open.
Tell me about that moment. What was it, night? Was it day? Were you in your shift or what?
Oh, gosh, was it night? I guess it was evening. Yeah, it was evening, and I was crossing. It was close to the time I was crossing over with my co-chief, and so we were both on board then, which was super exciting for us to together, be kind of, I guess, heady with excitement about what we'd succeeded in finding at the peak ring, which was really cool.
So go ahead with the other discoveries.
Yeah, so I guess the next paper out of the gate, that was the next really big one, was this recovery of life at the impact site. That we discovered a fairly normal. We both found these trace fossils of burrowing organisms within the first meter bearing all the crater material, but then we actually found that as you moved up into the Paleocene for the next tens to hundreds of thousands of years to millions of years, that it was a very healthy ecosystem within the crater. There was no suggestion of any retardation of life, even though we were at ground zero. So that kind of said all of these hypotheses that had been put out in the past, that there was a delayed recovery of life as you approached where the impact site was, that those were incorrect. That really the global ocean came right back into the crater and brought with it surviving organisms that recolonized the crater right then and there. So that was exciting.
I see. And can you tell me something about the how the stratigraphy was before the impact. What is that the asteroid hit?
Yeah, absolutely. So it was about 3 kilometers, in some places even thicker than that, but at least 3 kilometers of limestones and also evaporites, so anhydrite and gypsum and things like that, so some sulfur-rich rocks. And the anhydrite, the evaporites were probably at least a quarter of the target, and, some places they may have even approached 50% of the target. But, it was dominated by sort of carbonate evaporite sequence. Which meant that when the impact hit, that the release of gases and particles would have been dominated, in fact, by carbonate particles and evaporites. So, one of our other goals, in fact, was to see if we could understand the inputs into the atmosphere caused by this impact. And in particular, it looks like one that may be quite important is the release of sulfur from the target because of all those sulfate-rich rocks, and combining that with sulfur combined with the water that was at the target makes sulfur aerosols, which might be a very significant way to be able to cool the Earth and inhibit photosynthesis in the wake of the impact.
So that was the reason why 2/3 or 3/4 of the species, they got extincted because of the pollution in the atmosphere?
Well, it's probably one of the most important kill mechanisms, but it's not the only one. I mean, within the day of the impact, in fact, you'd have raining ejecta coming in back out of the atmosphere all over the planet because it released a huge amount of material. And that ejecta, as it rained down through the atmosphere, heated up, and it probably caused some degree of wildfires around the whole world and heated up the land surface. So that would have been the first killer if you were, say, on the other side of the planet. If you were local, of course, you were killed by the blast wave for the impact itself, or if you're a little farther out, you were probably killed by the thermal radiation generated by the impact, or the tsunami if you were farther out from that. But if you're on the other side of the planet, then the kill mechanisms probably started with this ejecta raining down, setting things on fire, and so on. But then the longer term, and by longer term I mean the next few months to years, there were dust in the atmosphere, there was probably soot from the wildfires, and then there was this sulfate aerosols. And all of those together cause an enormous cooling. In fact, one of the latest climate models has the world dropping in temperature by 25 degrees Celsius everywhere, for years.
I see. And Sean, do you want to go ahead? You were enumerating the discoveries, maybe associated with the papers that you published. You said there were 13, and you just talked about 2 of them.
Yeah, that's right. So several others. We had a paper that just came out in Nature that talked in the last couple of weeks that talked about how is it that rocks can move like a fluid without actually being melted. What is that? How physically is that possible to create these wide, flat impact craters like we see on the Moon and Mars and like Chicxulub is? And it turns out that it's done through fracturing at all scales. So all the way down to fracturing at the scale of a crystal, all the way up to large blocks moving around at maybe the 100 meters of scale. And so in our core, we saw faulting at all scales, and we could even discuss sort of an overprinting of faults originally generated by the shock wave, or fractures generated by the shock wave, to fractures that, as the rock sort of regains some strength, how it kind of, you go from cataclasites, like you might see in an earthquake rock, up to regular-looking faults as time progressed. And this sort of overprinting of styles of structural deformation turned out to be the physical evidence of this movement of these rocks, first 10 or 20 kilometers out, and then 10 or 20 kilometers up, and then 10 kilometers back to form the peak ring. So they, in something like 10 minutes, the rocks in the peak ring moved at least 30 kilometers, which is phenomenal, without actually melting in the process.
Sean, you have a spectacular data set. You have pressure from your the society in general, because they want to know about this. How do you decide what is worth it to publish, and when is the right moment to publish?
Yeah, that's a great question. I mean, we spend a lot of time just trying to figure out all of our data and then package it up very carefully, into coherent publications on different topics. So, I've mentioned 3. We also have a paper that's currently in review on the hydrothermal system that existed. So that, the incredible hydrothermal system that was kicked off by the crater. We have a paper in review about microbial life that is currently living in the crater that evolved in the subsurface from life that almost certainly took advantage of that hydrothermal system. And then I'm about to submit a paper, in fact, it's on the screen in front of me here, that will be talking about the events of the very first day of the Cenozoic, because we have about a 130-meter section of rock basically generated within a day, which is kind of phenomenal to think about as a geologist. But it also records all these incredible processes that happened within that first day and tells us something about sort of the way impacts work in general, and some of the effects they can have both locally and distally.
So tell us more about when you decide that is the right time to publish. How is your thought process? Do you go backwards? So you say, okay, this is what I discovered, this is the conclusions, and then I go backwards deciding which kind of data to show because I have too many data to show.
Well, part of it is actually, when you have, 32 members on the original team and now we've grown to 80, you've got huge numbers of opinions of what the data actually means. So part of the timing of publications is breaking off a piece, getting somebody to lead that piece, and then getting everybody to discuss and decide, exactly what we want to say and come to an agreement that the data that we have, the rocks that we have, are saying what, And once we can kind of come to that agreed upon set of conclusions, then we can push a paper out the door on a particular one of these many topics that we're attacking. And so some of them were obvious, as soon as we could get some DNA out of microbes in the crater, well, there was going to be a paper saying what they were, things like that. But there are others that are still in debate. We're still discussing exactly what some of these data mean. For instance, a paper that's yet to come is one that's going to be looking at, do we have any iridium anomaly within the crater, which is a hard thing because unlike the other side of the world where everything is nice and condensed and you could find this iridium layer within a centimeter of clay. In the crater, it's much more dynamic, and we've got to figure out exactly how to interpret the record.
And something delicate as co-authorship. When you say that you are 32 people now growing to 80, how do you decide that? Because as we know now, academia requests researchers, professors, students to publish simply because that is the mechanism to move on in the profession.
Well, for the first, I think out of the 13 papers that we have out right now, or in review, or so on, the vast majority of them have everybody as a co-author. Not everybody from the 80-person group, but at least everybody from the 32 that originally went and got the data and then in Mexico and then spent a month in Germany doing all of the analyses of the cores as we split them open one by one, and we measured their physical properties and we described the cores and we did the geochemistry and the paleomagnetic measurements and so on and so forth. So that 32 people that devoted a month of their lives to studying the cores at a core lab in Germany, all of them have been co-authors on every one of these first set of papers, and then the additional people who've done the work on the specific topic of a given paper have also been co-authors. So I'd say most of our papers have co-authorships in the number in the 40s.
I see. Now, Sean Gulick, research professor at Jackson School of Geosciences, part of the University of Texas in Austin, here talking with us at Mini Geology. Sean, I would like to ask you about the other big asteroids impacts, because other asteroids that have hit Earth in the past,
sure,
leaving their marks, for instance, maybe in the Chesapeake Bay in the U.S., in the East Coast or in Germany, in Bavaria. However, they didn't cause mass extinctions like this one, at least as far as the fossil record shows. Why is that?
Oh, that's a great question. So I think part of it is a sense of scale. Of the three biggest impacts on Earth, we have Chicxulub at 200 kilometers. We have Sudbury crater in Canada, which was probably originally 200 kilometers or so across. And then we have an even bigger one, Vredefort, in South Africa. But Vredefort and Sudbury both happened about 2 billion years ago. So not much of a record of an extinction associated with them. And then the next one of that scale is Chicxulub, which did cause an extinction. Now, if you look at the next scale down craters, if you look at things like Chesapeake, for instance, which is 85 kilometers across, it apparently wasn't big enough or didn't release enough volatiles into the atmosphere, for instance, to really cause any problem other than being a really bad day if anything lived in the Chesapeake at the time. So that it's kind of fascinating. It takes a certain degree of an impact, but then maybe it also takes a particularly bad target to hit. Such as this carbonate evaporate rich target that the Chicxulub asteroid hit.
Why do you say it's a bad target?
Well, bad for life, good for us, as humans who get to evolve from the life that made it, but bad for the life that lived on the planet at the time. If you have a whole lot of climatically active gases released, by a geologic event, then the chance of causing global effects are much greater. Another good example is there's a good chance that the end Permian extinction was related to the Siberian trap volcanism. And the Siberian traps actually erupted through enormous coal seams and generated an extremely large amount of climatically active gases from those eruptions over the space of at least hundreds of thousands, if not millions of years. And that continued production of high degrees of climatically active gases may well have driven the extinction at the end of the Permian. But other volcanic eruptions of significance, such as, maybe the Columbia River one, for instance, did not necessarily generate extinction events. So I think it does matter how big it is, how quick it happens, and exactly what it releases as to whether or not it rises to the level of a mass extinction event.
So you enumerated a lot of discoveries that could be used by the scientific community in general for their own studies. I was wondering if, now that we see that this specific crater has something very special on the process, on how it formed, if all the studies you have done could be used as an analog to study other craters.
Well, certainly from the standpoint of impact processes, I think definitely. Now I think because it is the best preserved large impact crater on Earth, the next really well preserved peak ring crater is on the moon. So and it's a little cheaper to stay here on Earth. So from that standpoint, it was a chance to understand, how the landforms of a large impact crater, in fact, definitely form. Also, to better interpret the geology of craters that we see on Mars or a moon or Mercury, for instance, largely from remote sensing observations, from satellites and things, but to be able to interpret those better as a geologist. I think that's a really important role of studying things like impact craters on Earth as sort of analogs to understanding how we can study them elsewhere. And likewise in the sort of search for life, beyond Earth, this is also a critical question because I think we now can understand how the impact process can generate a habitat through the hydrothermal system and things like that, and exactly where we might expect to find life, like microbial life, for instance, taking advantage of such a system based on our study of an active system here on Earth.
Sure. When you have such a unique database, that the one that you 32 or 80 people are working on, Is it open also to other independent groups that they may have other ideas, other theories in order to prove them?
Well, I mean, absolutely. The data, because the data was, collected by effectively funding that's stemmed from taxpayers of all these countries. That data after a couple of years, actually after about a year, was made wide open. So you can access the cores. They are located at Texas A&M University's core repository that they run for the International Ocean Discovery Program. So they, data samples and so on can be requested to do research, and certainly there's opening, if you will, for many ideas in this that are well founded and have done their homework as to the work that's been done before.
And to your knowledge, is there any different theory that contrasts to what you and your team are supporting?
Well, sure. The leading alternative theory is that was that the Deccan traps, the volcanic events that were going on in India at a similar time frame, might have been the cause of the extinction, or that it was something like a 1-2 punch. And there are still there's a few people still arguing that in the scientific community that it was just the Deccan traps, but that's very few. Because the timing doesn't really work out. There are now some people who would argue that perhaps there was a bit of volcanism happening before, but then the impact hit and it actually caused additional volcanism to happen at the Deccan traps, and that additional volcanism continued for the next few 100,000 years. And so some people have argued that that's important for the extinction. I think many people who work on the Chicxulub crater and who work on the Cretaceous-Paleogene boundary more generally kind of disagree with that idea, because this extinction event is somewhat unique in all of the Earth's extinction events, in that it's the sharpest that we have in the fossil record. It's basically, things look like they were doing quite well. I mean, there was the sort of standard amount of background extinctions happening, and then but no more than that. No suggestion of a really stressed system, except for in, a few groups that have very small numbers of fossils. And then we get up to 66.0, and boom, everything changes. And then there's not really a suggestion of a second later short-term extinction. Instead, the sort of an extinction event and then a slow recovery of life afterwards seems to be the what the fossil record tells us, and that's quite different than like the end Permian extinction, where you could see a degradation of the environment, over a much longer period of time that totaled up to a very large mass extinction event, but not knife sharp in the fossil record like the Chicxulub one was.
And what are the parts of the study that they are still not clear, or there's space for inferences or even speculations? What is that has to be defined yet?
Oh, yeah. Well, there's so much more to do in the end. One is to look in much more detail at what exactly occurs to rocks during the impact cratering process. Much more to do on understanding and modeling the hydrothermal system that is generated to explain many of these unusual observations that we have within our cores, and to understand better the ecosystems that evolved both in the water above the crater afterwards, as well as within the subsurface of the crater, and how and if these sort of environments talked to each other at all. So those are key. And then I think it's worth going back to Cretaceous-Paleogene boundary outcrops and cores around the Gulf of Mexico and globally with some fresh perspectives that we have gained from looking directly in the crater as to what happened at ground zero. I think that's a really important next step that we should work on. And then, of course, looking maybe 10 years down the road, I'd like to drill again.
So yeah, I was thinking about where is your future? Sean. Do you see yourself as working on the hard data for a long time?
Yeah, I mean, working on the Chicxulub crater is sort of a third of my current research program, but I'd like to keep it that way if possible. And in particular, I think it would be very exciting to go and drill actually in the center of the crater offshore. Because that's where you could find the really thick melt sheet that gets generated in the center of large impact craters. So in the case of Chicxulub, we think that, beneath about a kilometer of sediment that has buried the center of the crater, including, perhaps an expanded recovery of life section, beneath all of that, we would find a 3 kilometer thick melt sheet generated directly by the impact. And that would be super exciting to drill down and actually sample those rocks and understand those processes as well.
So, sure, you mentioned that this is just 1/3 of your research, and I know you also study and research on tectonic events, but some of them, some of the topics you study, they may be related to this concept of catastrophism. Catastrophism in the geologic record, which include the impact cratering, the tectonic events, hurricanes. Do you want to talk about catastrophism and the importance of the philosophy behind this concept?
Yeah, sure. I'm not sure about the philosophy being the important thing. I think more that maybe that we have to be careful not to only perceive the world and the record of the Earth history in one way, right? So I think we have gotten used to and trained as geologists to think about sort of a steady state series of processes that take place, such as erosion that takes place over a long period of time, or deposition of sediments, creating sedimentary rocks, creating stratigraphy that occur over a very long period of time, right? In the sort of steady state set of processes, the uniformitarianism, if you will. But the alternative view is that individual events can be significant enough to affect the geologic record in a very profound way. So obviously, the Chicxulub event made a global stratigraphic horizon that can be found everywhere it's well preserved, and it is a catastrophic event. So in effect, it's our best example of sort of catastrophism also being important to consider in the history of the Earth. And even in any given single local place, if we look at an outcrop, let's say, of a coastal environment, we have to ask ourselves, are we seeing the day in, day out coastal processes, or are we really recording the winter storms only, or are we in fact sometimes recording the once in every 5 or 10 year hurricane as what's recorded back in the rock record? And I think we don't know the answer to that question very well, or we don't know how much of a percentage to attribute to these different processes yet. And it's something that is an active area of research on a lot of fronts and in a lot of environments right now.
Sean, we are reaching the end, and I would like you to leave the open mic if you want to talk to the audience, if you want to talk about ideas you have or shout-outs. So the mic is open for you.
Okay, I appreciate that. Well, I guess the shout-out, first of all, is to thank all of the funding efforts on the part of the National Science Foundation and all the other international science organizations that are basically part of governments everywhere that allow something as exciting as the International Ocean Discovery Program to actually persist and be able to do these really exciting science projects where there's not necessarily an immediate payoff, but rather a long-term, better understanding of the Earth system and life on it, including ourselves. And then the other shout-out, of course, is to the team. To my co-chief Joanna Morgan, to all of the scientists throughout the many universities around the world who've been a part of this, and to the hardworking folks on the lift boat Myrtle who were home for 2 months, and to the drilling crew from the DOSEC that actually brought us back the fantastic course. So those are important shout-outs, and I guess other than that, I'd like to just put a plug in for basic exploratory research being an important human endeavor.
Thank you very much. We were talking with Sean Gulick, research professor at Jackson School of Geosciences, part of the University of Texas in Austin. And this is Daniel Minizini, your inquisitive geologist here at KPFT HD2 channel with Mini Geology, the program that investigates on geology and the relationship with society. You can write me at minigeology@gmail.com, and you can listen to this program again in the YouTube channel, minigeology.com. And I really hope that you enjoy, Sean, as well. And please tell your students and your crew around you to listen to the program and to participate. This is open to everybody, so you're always invited in here.
Thank you very much.